the addition of dopants not only changes the number of carriers in a piece of silicon, but also the probability of finding an electron in a given state. With the addition of extra electrons in the conduction band, the probability of finding an electron in the conduction band increases. Recall the probability of finding an electron in a state of energy E in the conduction band is given by the Fermi Dirac function shown here. As the temperature is the same, the shape of the Fermi Dirac distribution function remains the same. The change in probability will be reflected by a change in the Fermi level EF. For N-type silicon, it will move up to indicate the higher probability of finding an electron in the conduction band. To give a reference for the location of the new Fermi level after doping, we usually use EI to mark the Fermi level of the intrinsic silicon. Let's try to find out the location of the Fermi level. Remember that the number of electrons in the conduction band is just equal to the equivalent density of states at EC multiplied by the probability of the states being filled. The expression is given here. Or after the Boltzmann approximations, it becomes this one. In the case of doped silicon, we actually know the number of carriers, which is just equal to the amount of dopants added. The unknown is actually the distance between EC and EF. And this can then be found by using the expressions kT times the natural log of NC over ND. Sometimes it is a bit difficult to remember the value of NC, and people usually refer to EF by its distance from EI instead of EC. It is also more convenient for using EI and NI as a reference due to the symmetry in the band diagrams between N-type and P-type semiconductors. Starting from a doped semiconductor with the Fermi level EF, its carrier concentration in the conduction band is given by Nc times e to the power of negative Ec minus Ef over kT. In the case of intrinsic silicon with Ef equal to Ei, the number of carriers in the conduction band is given by Nc times e to the power negative Ec minus Ei over kT. Dividing the first equation by the second one, we get N equal to Ni times d to the power of Ef minus Ei over kT. The unknowns in these expressions are N and the distance of Ef from Ei. With these expressions, you can find Ef if N is known and vice versa. This expression probably is the one that you will be using most often. There are many expressions relating to Fermi level and the carrier concentrations, but do not let them confuse you. They all come from the same basic principles after some mathematical manipulations. For a p-type semiconductor, the equations that relate the Fermi level and the number of holes with respect to the intrinsic silicon is given by the expressions P equal to Ni times d to the power Ei minus Ef over kT. Before we move on, let's do a simple exercise. Consider an N-type silicon material. Its energy band diagram is shown in the figure, where the donor level is marked explicitly as ED here. Try to draw the location of the Fermi level when the temperature of the silicon material is at A. 0K, B. 300K, C. 1200K, or at a very high temperature. Let's stop here and think about it for some time before viewing the video that tells you the answer.